Bismillahirrahmanirrahim. Dear students, in this week we will solve some more problems related to direct method of plotting shear force diagram and bending moment diagram. So let's start our first problem. In this problem, we have a simply supported beam and the beam is subjected to a UDL partly. The UDL ends here. And there is a point moment acting in counterclockwise direction. The magnitude is 5 kilonewton meter, and there is a point load acting in the downward direction with a magnitude of 10 kilonewton. Oh, it seems to me that this pencil is not visible, very visible, so let me change the pen. Okay, so we have this beam. Yes, I think it's better now. Let me check the focus of the camera as well. Okay, I think it's better focused now. The intensity of the UDL is 10 kilonewton per meter. Point moment 5 kilonewton meter, and point load 10 kilonewton. Okay, then we have these distances. Okay, the first one is 5 meters, then 2 meters, 3 meters, and 2 meters. We can label this point as point A. This is point B, C, D, and E. What else? We can call this reaction as RA and this reaction as RE. So this is the given situation, and our objective is to plot shear force and bending moment diagram using the direct method. For that, first step is to calculate the reactions, and we know that the reaction calculation is same as that of the method of equations. So let's apply the conditions of equilibrium. Sigma Fy equal to 0, and our convention will be we'll take upward forces as positive. So what are the forces acting in the upward direction? RA and RE. So both will be taken as positive, and then we have this UDL acting in the downward direction. So minus 10 into 5 is the UDL, and the 5 kilonewton meter is the moment. It will not appear in this equation. And then we have 10 kilonewton force acting in the downward direction, and that is equal to 0. If we rearrange this equation, we get RA plus RE equal to 60. Let's call this equation as equation number 1. And then if we apply sigma ME equal to 0, and our convention is we'll take clockwise movement as positive. So we are taking sum of movement about point E. Let's start from point A. RA is acting in upward direction, and it will produce clockwise movement about point E. So RA into the lever arm, that is 12, and it is clockwise, so it's positive. Then this UDL is producing movement in counterclockwise direction, so it will be negative. Resultant of the UDL is 10 into 5. And how much is the lever arm? 2 plus 3 plus 2 plus 2.5, because the resultant will act at the center of this UDL. So it will make 9.5. And then we have this movement which is acting in counterclockwise direction, so minus 5. And then moment because of this force 10 kilonewton, it will also generate movement in a counterclockwise direction, so it should be taken as negative, minus 10 into 2, and this should be equal to 0. Now if we solve this equation, we will get the value of RA, and how much is that? It is 41.67 kilonewton. So this is the value of reaction at support A. Then if we plug in this value in equation number 1, we can calculate the value of RE, and from that equation RE comes out to be 18.33 kilonewton. So now we have values of both the reactions. Now in this method, next step is to draw the shear force diagram and bending moment diagram, as we discussed in the last lecture, and we solved a couple of problems as well. So we know that in this method we do not need to consider every portion separately and draw bending moment, draw free body diagram, then write down equation of shear, moment, and calculate the values. So although that lengthy calculation is not required in this method. Reactions are calculated, we will directly jump to the plotting of shear force and bending moment diagram. So let's see how these diagrams can be drawn. For that, we'll have to draw the beam once again. So we have this UDL acting from point A to point B with a magnitude of 10 kilonewton per meter, and we have a point moment 5 kilonewton per meter, and we have a point load acting in the downward direction with a magnitude of 10 kilonewton. C, D, and E. Reactions are known now. RA is 41.67 kilonewton and RE is 18.33 kilonewton. And let me mark the distances as well. This is 5 meter, 2 meter, 3 meter, and 2 meter. So let's draw the guidelines for the plotting of shear force and bending moment diagrams. Okay, here are the guidelines. This is our 0 line for SFD, and our units are kilonewton. Okay, so let's start from the left end. At the left end, at point A, we have this reaction 41.67 acting in the upward direction. So from 0, we will move in the upward direction up to 41.67. 41.67. Okay, and then we have this UDL, and UDL is acting in the downward direction, so its area will be taken as negative. So plus 41.67 minus the area of UDL, which is equal to 10 into 5 equal to 50. So 41.67 minus 50, and this brings us to 8.33 kilonewton. Be somewhere over here. Somewhere over here. Okay, so as the load is area load, so it's a UDL, so shear force diagram in this case will be first degree. On the left side it is 41.67, and on the right side it is 8.33. And then from point B to C there is no external load acting, so shear force diagram will remain constant. Go straight, 8.33. Whenever you have a 0 degree line, it is not mandatory to write down the value at every point. You can see that's a straight line, a 0 degree line, so it's 8.33 here, it's understood to be 8.33 here. If you want, you can write it down, but it's not mandatory. And then we have a 5 kilonewton per meter moment at this location. Now we already know that moment does not reflect in shear force diagram. So at this location the value of shear force will remain constant, and then from C to D there is no additional external load acting. So the shear force diagram will again remain straight. It will be a 0 degree line, and we'll reach at 8.33. Now at this point, at point D, there is a load 10 kilonewton acting in the downward direction. So 8.33 minus 10, this will bring us to 18.33. 18.33 kilonewton. And then from D to E there is no external load acting, so the shear force diagram will remain 0 degree, and we will reach point E. And at point E we have a reaction that is acting in upward direction with a magnitude of 18.33. So if we move in the upward direction equal to 18.33, we will come to 0. So in this way the shear force diagram is closed, and this means that our shear force diagram is correct. So this part is positive and this part is negative. Now in this SFD we have a point of zero shear, and we know that whenever we have point of zero shear in our diagram, we need to identify that point. To identify this point, we have two possibilities. One possibility is that we can write down the equation of shear for portion AB, and then we can put it equal to 0. That will give us the location of this point. Or if we have a situation in which we can compare the similar triangles, for example in this case we can do that, so we can follow that approach as well. So I think comparing the similar triangles would be a simpler option, so we will follow that approach in this case. So we can assume this distance to be x, then this distance is 5 minus x. 5 minus x. So now we can compare these two triangles. 41.67 divided by x should be equal to 8.33 divided by 5 minus x. And we know that we can solve such equations directly on our calculators, or if you want you can simplify this in this, then get the value of x. So whatever you like. So if we solve it, we will get the value of x as 4.167. The value of x that we get from this equation is 4.167. So this is 4.167. So similarly, we can calculate how much is 5 minus x. Okay, so point of zero shear is located. Now let's move to the plotting of bending moment diagram. And this is our 0, 0 line. We are plotting BMD and our units are kilonewton meter. Okay, we need to draw another guideline here. For bending moment diagram, when we start from support A, we can see that at support A we have a hinge support and there is no externally applied moment. So the moment at support A will be equal to 0. So we'll start from this point, and then in order to get the value of bending moment at this location, at the point of zero shear, we will have to consider this area, this positive area. And this positive area can be easily calculated by simply 41.67 into 4.167 divided by 2. It's the area of this triangle. So if we calculate this, we get 86.82. So the value of moment at this point is 86.82, and the magnitude of shear is decreasing in this direction, so the slope of bending moment diagram should also be decreasing. Here, so we have a second degree curve and as we move from point A to B, the slope of the second degree curve is decreasing. Now, in order to move from this point of zero shear up to point B, we need to subtract the area of this small triangle, and we know that x is this base of the triangle is 5 minus x. We know x. Perpendicular of the triangle is also known, so this side into the base of the triangle divided by 2 will give us the area of the smaller triangle. And if we subtract this area from this value, which is 86.82, let me write it down here, 86.82, then we'll get the value of bending moment at this location. This is also a second degree curve, and how much is the value? It is 83.35. 83.35. Now from this location at point B, in order to move to point C, we will have to calculate the value of this area. This is a rectangular area. Vertical side is 8.33, horizontal dimension is 2 meters. So 83.35 minus 8.33 into 2, that will give us the value of bending moment at point C. So if we do that, we get 66.69. 66.69 kilonewton meter is the value of bending moment at this location. Then at point C, we have a moment acting, and as we discussed earlier, that whenever we are drawing bending moment diagram, we need to keep an eye on the loading, because the effect of moment does not reflect in the effect of point moment does not reflect in shear force diagram. So from 66.69, this 5 kilonewton meter moment is acting in counterclockwise direction. So according to our convention, this is negative. So 66.69 minus 5 brings us to 61.69. 61.69. I've written it inside the diagram. Preferably we should write it down on the outer side, outside the diagram. And then from 61.69, if we subtract this area, which is 8.33 into 3, we will get the value of bending moment at point D. And how much is that? That is 36.7. 36.7. And this is a straight line. Okay, and 36.67 is positive. Then subtract this area from 36.7. So 36.7 minus 18.33 into 2, and this should give us the value of moment at this point. And if you calculated this the value of moment at this roller support, sometimes you may get a very small value like point something, that or 0.0 something. That small value, very small value, appears because of the rounding off error in our calculations. So if this value is very small, you can take that as 0. For example, in this case 18.66, if you multiply that with 2, you will get 18.33. if you multiply that with 2, you will get 36.66, whereas the value here is 36.7. so if you take the difference, you will get 0.04 as the remainder. So we can just simply ignore that. So we'll say that after subtracting this area, our diagram is closed. This brings us to 0. 0 means our bending moment diagram is also correct, and the entire bending moment diagram is positive. So this completes the solution of this problem. We have drawn its shear force diagram and bending moment diagram. I haven't drawn the elastic curve, but we know that the entire bending moment diagram is positive. So the elastic curve will simply be a sagging curve. All right. Okay. So at this point, I'll stop recording. Thank you very much.